Hello friends, welcome to this YouTube channel. Today we are going to solve a pair of numerical problems on gross efficiency and developed torque of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of circuit parameters are given. A 6-pole 115 volt 60 Hz three-phase star-connected induction motor has following per phase parameters referred to stator side. Stator impedance 0.07 plus J times 0.3 ohm. Rotor standstill impedance 0.08 plus J times 0.3 ohm. Magnetizing branch has G0 equals to 0.022 mho and B0 equals to 0.158 mho. We have to determine equivalent rotor current, stator power factor, gross power output, gross torque and gross efficiency by using approximate equivalent circuit at a slip of 2%. Let us first write down the given data. Line to line terminal voltage VL equals to 115 volts. For star connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 115 divided by root 3, that is equal to 66.3953 volt. Given stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.07 plus J times 0.3 ohm and standstill rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus JX2S dash equals to 0.08 plus J times 0.3 ohm. At any value of slip S, expression for rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 2%, that is equal to 0.02 per unit. Therefore, Z2 dash equals to 0.08 by 0.02 plus J times 0.3 ohm. That gives us 4 plus J times 0.3 ohm. Let us now determine equivalent impedance per phase referred to stator side. ZEQ equals to Z1 plus Z2 dash. Using values we get 4.07 plus J times 0.6 ohm. This may be written in polar form as 4.114 ohm at an angle 8.386 degree. Now we shall determine rotor current per phase referred to stator side. I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 66.3953 at an angle 0 degree divided by 4.114 at an angle 8.386 degree. That gives us 16.14 ampere at an angle minus 8.386 degree. Given per phase conductance of the shunt branch G0 equals to 0.022 mho and per phase inductive susceptance of the shunt branch B0 equals to 0.158 mho. Per phase admittance of the shunt branch Y0 equals to G0 minus J times B0, that is equal to 0.022 minus j times 0.158 mho. This may be written in polar form as 0.1595 mho at an angle minus 82 degree. Expression for no load current per phase I0 equals to Et into Y0. Using values we get 66.3953 at an angle 0 degree into 0.1595 at an angle minus 82 degree. That gives us 10.59 ampere at an angle minus 82 degree. This may be written in Cartesian form as 1.4738 minus j times 10.487 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 16.14 ampere at an angle minus 8.386 degree. This may be written in Cartesian form as 15.9674 minus j times 2.354 ampere. Applying Kirchhoff's current law at node P, we get stator current per phase I1 equals to I0 plus I2 dash. Using values we get 17.4412 minus j times 12.841 ampere. This may be written in polar form as 21.6584 ampere at an angle minus 36.3622 degree. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi1 equals to 21.6584 ampere at an angle minus 36.3622 degree. For star-connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 36.3622 degree, that is equal to 0.8053. Lagging. For three-phase induction motor, total input power Pin equals to √3 times VL into I1 cos phi 1. Using values we get √3 into 115 into 21.6584 into 0.8053, which is approximately equal to 3474 watts. Now we shall calculate equivalent load resistance referred to stator side. RL dash equals to 1 upon S minus 1 into R2 dash. Given slip S equals to 0.02 per unit and per phase rotor resistance referred to stator side R2 dash equals to 0.08 ohm. Therefore, RL dash equals to 1 upon 0.02 minus 1 into 0.08, that is equal to 3.92 ohm. Now we shall calculate total gross power output. PM equals to 3 times I2 dash square into RL dash. We have obtained rotor current per phase referred to stator side I2 dash equals to 16.14 ampere. Therefore, PM equals to 3 into 16.14 square into 3.92, which is approximately equal to 3063.5 watt. Given number of poles of the machine P equals to 6 and supply frequency F equals to 60 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 60 divided by 6, that is equal to 1200 revolutions per minute. Expression for rotor speed Nr equals to 1 minus s times ns. Given slip s equals to 0.02 per unit. Therefore, Nr equals to 1 minus 0.02 into 1200, that is equal to 1176 revolutions per minute. Expression for gross efficiency of the motor eta G equals to Pm divided by Pin. We have obtained gross power output Pm equals to 3063.5 watt and total power input Pin equals to 3474 watts. Therefore, eta G equals to 3063.5 divided by 3474, that is equal to 0.8818 per unit or 88.18%. Expression for gross torque Td equals to Pm divided by 2 pi into Nr by 6T. Using values we get 3063.5 divided by 2 pi into 1176 by 6T, that is equal to 24.876 Newton meter. A 4-pole 415 volts 50 Hz 3-phase star connected induction motor has per phase stator impedance Z1 equals to 0.06 plus J times 0.2 ohm and standstill rotor impedance per phase referred to stator side Z2S dash equals to 0.07 plus J times 0.4 ohm. The per phase magnetizing reactance is 10 ohm and resistance representing core loss is 40 ohm. The slip is 3.6%. Using approximate equivalent circuit, we have to calculate rotor speed, stator current and its power factor, developed torque and gross efficiency of the motor. Let us first write down the given data. Line to line terminal voltage VL equals to 415 volts. For star connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 415 divided by root 3, that gives us 239.6 volt. Given stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.06 plus J times 0.2 ohm and standstill rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus JX2S dash equals to 0.07 plus J times 0.4 ohm. At any value of slip S, rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 3.6%, that is equal to 0.036 per unit. Therefore, Z2 dash equals to 0.07 by 0.036 plus J times 0.4 ohm. That gives us 1.9444 plus J times 0.4 ohm. Now we shall calculate equivalent impedance per phase. ZEQ equals to Z1 plus Z2 dash. Using values we get 2.0044 plus J times 0.6 ohm. This may be written in polar form as 2.0923 ohm at an angle 16.6646 degree. Expression for rotor current per phase referred to stator side I2 dash equals to Et divided by Zeq. Taking terminal voltage per phase Et as reference, we get I2 dash equals to 239.6 at an angle 0 degree divided by 2.0923 at an angle 16.6646 degree. That gives us 114.5151 ampere at an angle minus 16.6646 degree. Let us now calculate working component of no load current per phase. IW equals to Et divided by RC. Given per phase resistance representing core loss, RC equals to 40 ohm. Therefore, IW equals to 239.6 divided by 40, that gives us 5.99 ampere. Magnetizing component of no load current per phase, Im equals to Et divided by Xm. Given per phase magnetizing reactance, Xm equals to 10 ohm. Therefore, Im equals to 239.6 divided by 10, that gives us 23.96 ampere. Expression for no load current per phase, I0 equals to IW minus J times Im, that is equal to 5.99 minus J times 23.96 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 114.5151 ampere at an angle minus 16.6646 degree. This may be written in Cartesian form as 109.71 minus J times 32.84 ampere. Applying Kirchhoff's current law at node P, we get stator current per phase I1 equals to I0 plus I2 dash. Using values, we get 115.7 minus J times 56.8 ampere. This may be written in polar form as 128.89 ampere at an angle minus 26.1476 degree. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 128.89 ampere at an angle minus 26.1476 degree. For star-connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 26.1476 degree, that is equal to 0.8977 lagging. For three-phase induction motor, total power input Pin equals to root 3 times VL into I1 cos phi 1. Using values, we get root 3 into 415 into 128.89 into 0.8977, that is equal to 83,168.558 watt. Expression for total air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given slip S equals to 0.036 per unit and per phase rotor resistance referred to stator side R2 dash equals to 0.07 ohm. we have obtained rotor current per phase referred to stator side I2 dash equals to 114.5151 ampere. Therefore, Pg equals to 3 into 114.5151 square into 0.07 by 0.036, that is equal to 76,496.631 watt. Total mechanical power developed Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.036 into 76,496.631, that is equal to 73,742.752 watt. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that is equal to 1500 revolutions per minute. Rotor speed Nr equals to 1 minus S times Ns. Given slip S equals to 0.036 per unit. Therefore, Nr equals to 1 minus 0.036 into 1500, that is equal to 1446 revolutions per minute. Expression for developed torque Td equals to Pm divided by 2 pi into Nr by 60. We have computed total mechanical power developed Pm equals to 73,742.752 watt. Therefore, Td equals to 73,742.752 divided by 2 pi into 1446 by 60, which is approximately equal to 487 Newton meter. Now we shall determine gross efficiency of the motor. Eta G equals to Pm divided by Pin. We have obtained total power input. Pin equals to 83,168.558 watt. Therefore, eta G equals to 73,742.752 divided by 83,168.558. That gives us 0.8867 per unit or 88.67%. So today we have solved a pair of numerical problems on three-phase induction motors. By solving these problems, we have learned how to determine gross efficiency and develop torque of a three-phase induction motor for a particular value of slip using its per-phase approximate equivalent circuit when values of circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.